So, we're going to start in this week on looking at various techniques for computing antiderivatives and then using those techniques with the fundamental theorem of calculus to solve definite integrals. The first technique that we're going to look at, because we already know some techniques, we have basically you recognize a derivative, so you can write down its antiderivative, or you use substitution. And those are really the two most important techniques. But there's a bunch of other techniques, and those are what we're going to start covering now, that you also need to be able to use, because honestly, trying to find antiderivatives is a bit of a tricky problem in general. So the more techniques we have, the better. Now here's the nice thing. Everything we know about derivatives, every rule for derivatives has a corresponding rule for antiderivatives. And the one that we're going to look at today is going to be, what do you do with the product rule? First of all, you figure out this is not the pen that I was looking for. This pen is kind of terrible. There, that one is a little better, I think, hopefully. So remember, what the product rule says is that if I want to take the derivative of f times g, this is f prime g plus g prime f. Now, I'm going to write this out in a slightly different way that's a bit more convenient. I'm going to write this using differentials. The differential of f times g is then g df plus f dg. Remember, a differential is just the derivative times dx. And differentials play a big role in integration. In fact, what we integrate are differentials. We don't, strictly speaking, integrate functions exactly. They have to be, it's like a function with a differential. We talk about integrating functions, but strictly speaking, there has to be that differential on the end, and so we're really integrating a differential. Now, what this means then is if I take the integral of the differential of fg, this is going to be equal to the integral of g times the differential of f plus the integral of f times the differential of g. And usually we end up rewriting this in a slightly different way. So the way that we usually end up writing this is we move this over to the other side and we say the integral of f times the differential of g is equal to the integral of the differential of f times g minus the integral of g times the differential of f. Also, by convention, instead of using f and g, we usually write this out in terms of u and v. Oh, and one other thing to notice, this integral right here, this is really just f times g, possibly plus a constant. So if I rewrite this in terms of u and v, I say the integral of u dv is equal to uv minus the integral of v du. And there we go. You might wonder, why didn't I bother putting a constant of integration here? Well, it's because this integral is going to give me a constant of integration anyway. And if I add two constants together, that's just a third constant. So when you're working with constants of integration and they get added together and stuff, then you can kind of just consolidate everything down to a single constant. Excuse me. I don't really need to have multiple constants, therefore, floating around. So this technique is called integration by parts. And it's one of the most useful techniques of integration that we can do. So let's take a quick look at some examples of using integration by parts. Now, the thing that you're going to want to do when you set up an integration by parts problem is you need to find your u, your v, your du, and your dv. And your goal, here's the key thing, when you do this process, what you want is you want to pick u to be part of your original integral, that when you take the differential, it gets simpler. And you need your dv to be something where you can relatively easily find the antiderivative in order to find v. Because remember, the things that you pick from the original problem are your u and your dv. And then from that, you're going to find your du and your v, but we need to be able to find those in a reasonably simple manner. You want to pick something where it's going to get simpler. That's really the key. So as an example of doing this kind of thing, let's suppose that I want to do the integral of x e to the x dx. Now, you first might try doing this by using, you might think about doing substitution, basically. Unfortunately, substitution doesn't work here. If you want to take a minute to think about all the different substitutions you can do and kind of convince yourself that substitution isn't going to help you, please feel free to take a minute to do that. You know, you could try some different things, but yeah, it turns out substitution is not going to help you. It would help if this weren't x squared. Then I could do substitution, no problem. But because it's just an x by itself, unfortunately, no. However, I can do this by integration by parts. And the way that I'm going to do this is I'm going to take my u to be equal to x. And I do that because then du just becomes equal to dx. On the other hand, that leaves me with e to the x dx for my dv. And the nice thing is that the antiderivative of e to the x is just e to the x itself. So that means that my v is quite simple to calculate in this case. It doesn't become something super complicated. Well, what can I do next? The next thing that I can do in order to try to figure this out is I can look at writing down uv minus v du. And we integrate the v du. So now we want to do uv minus the integral of v du. That is the rule for doing integration by parts. And at this point, I have all four of these things written down up here. I've got a little grid with all of the information that I need, and I can just go ahead and write them down. So uv, that's going to be x e to the x, and then I have to subtract the integral of v, that's my e to the x, and then du is the same as dx. At this point, this integral is actually straightforward. I can do this integral without any problems because we know the antiderivative of e to the x is just e to the x. So this is going to become x e to the x minus e to the x plus some constant of integration. If you would like to verify that this is correct, take the derivative of this answer that we got, and you will see it comes out to be x e to the x, which is what we were trying to integrate in the first place. So when you do one of these methods, in fact, when you're doing an antiderivative in general, you can always check your answers by taking the antiderivative that you found and making sure the derivative comes back to whatever you started with. So there is an example of using integration by parts. Here is another sort of example for integration by parts. Let's suppose that instead of just having x e to the x, let's suppose that I wanted to do the integral of, maybe I have something like x e to the 4x dx. Now this is going to be a little bit trickier, but not by much. It's a very similar problem, and I'm going to use a very similar approach. So I'm going to take, I need my u, my v, my du, and my dv. I'm going to take u to be equal to x again, and du then still becomes dx. I'm going to take dv to be e to the 4x dx, and that makes v into 1/4 e to the 4x. So that part is very important, right? We have this 1/4 e to the 4x that shows up here. And now what we're going to do is we're going to rewrite this as uv, so that's going to be 1/4 x e to the 4x minus the integral of v du. So that's going to be 1/4 e to the 4x dx. Once again, I can now do this part of the problem without much difficulty. This is going to become, first I have this 1/4 x e to the 4x, and then I'm going to have minus 1/16 e to the 4x. I could also, if I wanted to, I can actually factor this e to the 4x and rewrite this as x over 4 minus 1/16 e to the 4x. I could have done a factoring thing like that in the previous problem too if I wanted to. I didn't do it for some reason. I didn't think about doing it there. So yeah, we can always factor that sort of thing out. So you can see, here's another example very similar to the first one of using integration by parts. Now let's take a moment and think about how would I go about doing this if I were to need to kind of think about, like, what is this going to come out to be? Well, so how would I figure out what are u and v to take, basically? What is my u, what is my dv? Again, you want u to be picked so that its differential gets simpler. And you want dv to be something where you can find v by anti-differentiation in a hopefully semi-straightforward manner. So that is really your goal here in how you pick this. For instance, let me just take a moment and say, what if I had picked u and v differently? What if, for the sake of example, I had tried to do u equals e to the 4x, and then dv is equal to x dx? I could still find v. It would be x squared over 2. And that's okay, but it's getting more complicated, which isn't really a good thing. But then the problem is that du would come out to be 4 e to the 4x dx. And this is not simpler at all. This is actually just as complicated as I started with, plus I've got some extra coefficients floating around now. If I wrote down my new integrals, they would have become more complicated than what we started with, okay? So this is a situation where when I start seeing things get more complicated like this, see, this would become x squared over 2 e to the 4x minus the integral of 4x e to the 4x dx. Well, this is true. It's just not terribly useful because when I look at this, this new integral hasn't really gotten any better than the original integrals. And plus I've got this new, more complicated term floating out there. So this would suggest to me I've probably picked u and v poorly. Or rather, I've probably picked u and dv poorly. So I should probably go ahead and I should, rethink my approach. Let me give you guys a problem to think about here and see if you can figure out how to use integration by parts to deal with this. What if you wanted to do the integral of 2x sine x dx? So pause the video, take a few minutes to try to work this one out, and then come back and we'll work it together. All right, so what I'm going to do here is I'm going to pick my u to be 2x. That makes du into 2 dx. And I will pick my dv to be sine x dx. That makes v into negative cosine x. So it's a little bit like what we did with the e to the x, except this time we've got a trig function instead of an exponential. But it's a similar kind of idea here for what I'm picking. And let's see what I get when I do this. Well, uv is now going to be negative 2x cosine x. And then I'm going to be subtracting the integral of v du. So that's going to be negative cosine x, and then I'm going to have times 2 dx. So this becomes, and you'll have to excuse the sort of scrunched in writing here, this becomes negative 2x cosine x plus the integral of 2 cosine x dx. But we know how to find the antiderivative of cosine x. See, this integral is simpler than the one that we started with, and that's kind of my goal. I want to get something that is simpler than what we started with. So this is going to come out to be then negative 2x cosine x plus 2 sine x plus a constant, because the antiderivative of cosine x is just sine x. So hopefully you guys were able to figure that out. If you weren't, hopefully this explanation is able to clear up whatever was going on there for you. Now, a few things that we do need to note here. The situation with integration by parts can become more complicated in some cases because in some instances, we actually need to apply parts multiple times. And I want to show you an example of applying parts multiple times here. Suppose that I wanted to do the integral of x squared e to the x dx. Well, this is going to, when I pick my u and my dv, dv is going to be e to the x dx. That makes v equal e to the x. U is going to be x squared, which makes du 2x e to the x, or 2x dx. There we go. That makes my formula with parts into x squared e to the x minus the integral of 2x e to the x dx. Now, you might think, well, that's no good because we still don't know how to do this antiderivative here. But here's the thing. We've made this simpler. It used to have an x squared. Now it's just got an x. And that is a good thing. That means we might be getting somewhere. And in fact, that is exactly what's happening. We are getting somewhere here. We're getting closer to our goal. It's just in order to deal with this antiderivative, I'm going to need to use integration by parts on this guy. So what I'm going to do is I'm going to make a u1 v1 du1 dv1. In other words, I'm going to repeat this process again. My u1 is going to be 2x, so the differential becomes 2dx. dv1 is e to the x dx. Actually, that's the same as I picked for dv. That makes v1 still into just an e to the x. And that means this is going to become x squared e to the x. Then I'm going to have minus 2x e to the x. And then, remember, I'm subtracting this whole thing off. So we're going to have minus 2x e to the x minus the integral of v du. So that's 2 e to the x dx. That becomes x squared e to the x minus 2x e to the x plus 2 e to the x. And we can rewrite this as x squared minus 2x plus 2 times e to the x. So what we've done here is we've used integration by parts twice. Sometimes your first usage will make things simpler for you, but it won't be enough in and of itself to finish the problem. Sometimes you got to then go on from there and see if you can continue to figure out what exactly is going on. So hopefully you can see now what happened with this sort of thing. And the same sort of thing would happen if I had, say, an x squared times cosine x or something. There's plenty of situations where you might have to iterate this sort of thing. In fact, let me bring up something really quick. So one of the things that I want to look at here as a sort of example where you iterate things, and we're going to come back to this, but let's suppose that I have the integral of x to the k e to the minus x dx. Well, actually, do I want a minus 1 in here? I think by tradition, yeah. There is, for various reasons, we do x to the k minus 1 in here. If I want to do this integral by parts, what I can do is I can say, well, this is equal to, I take u to be x to the k minus 1. that makes du equal to k minus 1 x to the k minus 2 dx. If I then take my dv to be e to the minus x dx, that makes v into negative e to the minus x. So this becomes x to the k minus 1 e to the minus x minus k minus 1 times the integral of x to the k minus 2 e to the minus x, except this is actually negative e to the minus x, and so this just becomes a plus with a dx. So the signs, the minus signs cancel each other to give me a plus here. And you can then iterate this procedure, because now we have x to the k minus 2 instead of k minus 1. You can repeat this procedure and keep on going. It turns out that this particular integral is really, really important in something called the gamma function, which we will return to in a later class when we talk about improper integration. But I just wanted to mention this pattern is what's going to make it work, because it turns out what the gamma function is going to do for us is it's going to do something really funny. It's going to give us this function that, basically generalizes the exponential function. Or not the exponential function, the factorial function. It's going to generalize factorials. And the reason it ends up generalizing factorials is because of this iterative kind of thing, where it turns out at the end, you're just basically multiplying everything by k minus 1 factorial, and it turns out everything else works out nicely. But yeah, this pattern of integration by parts is what we're going to use in the future to do that. So that's sort of looking ahead to that kind of thing. Now, I want to take a look at some other examples of using integration by parts. So here is a good example that initially maybe doesn't look like you can do integration by parts, but actually, yeah, you can. Let's suppose that I want to find the integral of the natural log of x dx. Now, this is a bit weird because it doesn't look like it has a lot going for it, right? It doesn't really look like it's got pieces that I could break it up into. Actually, there is literally one way to break this thing up. The only thing I can do to break this up is to take u to be log x and dv to be dx. That makes v into x, and the differential of u is going to be dx over x, or 1 over x dx, depending on how you want to write it. So this is going to become x log x minus the integral of x times dx over x. These cancel, and this becomes x log x minus x plus a constant, which is of course just going to be x times log x minus 1 plus a constant. Oh, I think in one of my examples before, I may have dropped my constant of integration. Try not to do that. It's very bad to drop your constants of integration. But I think in the example I did with the iteration, I didn't really have room on the end, and so I forgot when I wrote, in fact, it's still up here, x squared minus 2x plus 2 e to the x. That should have actually had a constant of integration on it. I just kind of ran out of space. Anyway, so we've now been able to figure out the antiderivative of the natural log of x by using this method. And you can now figure out the antiderivative of any log with any base, like let's say log base 10 or log base 27 or whatever you want, because you remember that you can convert log bases. So you can rewrite any logarithm in terms of the natural log function, and then you can use this antiderivative in order to figure out your new antiderivative. Let me bring up one more example that I want to make sure is what I want. Yeah, so let's take a look at this example. Let's suppose that I want to do the integral of cosine squared x dx. I can actually think of this as the integral of cosine x times cosine x dx. And this is going to be, if I take my u to be cosine x and my du to be cosine x dx, then, I'm sorry, that's not du, this is dv, then v is going to be sine x and du is going to be negative sine x dx. So this is going to become cos x sine x, and then minus, but the negative here is going to cancel with it, plus the integral of sine x times sine x dx. Well, that doesn't seem to get us very far now, does it? But what I can do at this point is I can say, okay, now I'm going to play the same game here. I'm going to take u1 is equal to sine x. That makes du1 equal to cosine x. Then I'm going to take dv1 to be equal to sine x dx. And then I'm going to take v1 is going to be negative cosine x, and I can keep on rewriting this. So this is going to become cosine x sine x, and then we're going to have plus actually, this is not the example I was thinking of. Never mind. Let's work that out later. I'm going to skip that for now. So forget everything we were doing. We'll come back to that when we start talking about integrating trig functions, because there are tricks that we can do there, but actually that gets us a bit far afield from what I would like to do today. So let's scratch that for the moment and pretend it didn't happen. And we'll come back to it in a couple of lectures from now when we're talking about trig techniques. What I do want to show you is sometimes when you're doing these techniques, you do have to split the integral into something you do by parts together with something you do not by parts. So for instance, let's suppose that I want to do the integral of x plus 3 e to the x dx. Well, what I want to do in order to do this problem is I want to actually split this up into the integral of x e to the x dx plus the integral of 3 e to the x dx. The reason I want to do this is because I can now take this first integral and I can do this one by parts, and I can do this one without needing to do any parts at all. Although I guess if I wanted to, I could have actually done this whole thing by parts from the start by just sort of taking u to be equal to x plus 3, and that would have worked as well. But the point is, you can split this up so that you can do parts on different sections of this thing, and it'll work out. And you can see why this is going to work. We've done this example before, x e to the x, and we know how to do this because this is just a basic antiderivative. So we've split it up this way, and it allows us to work through this problem. Now, there are other situations sometimes where you might find yourself in a case where maybe different techniques will work. Sometimes you might find yourself in a situation where you can use substitution, but you could also use integration by parts. And in those cases, does it matter which one you use? No, not really. You can do whatever you want as long as it is something that works, okay? So use whatever works for you, whatever you like best. However, keep in mind that in many examples, only one of the techniques is going to work out for you. You won't necessarily be able to do either technique in either situation. All right, I know this was a bit on the short side, but this is kind of, I think, one of the simpler techniques we're going to talk about this week, so I'm going to end there and suggest that you take a look at all of the examples on the Paul's Math Notes page if you want to see some further worked out stuff here. So the other techniques we're going to do this week are going to be somewhat more complicated. And yeah, like I said, we're going to come back to that because That trig example I wrote down, it gets kind of annoying. But we will work that out in one of our future lectures here.